spins of multitudes of materials. Don't worry about what DNP and MR means just yet. We'll go into that later. So here's how this talk will spin. So first, I'm going to go through some of my past challenges and backgrounds so that you get an idea of where I'm coming from and some of the lessons I've learned that may be helpful to you. Then I'm going to go into the motivation of my research, so that way you understand why I do the research I'm doing. Then I'm going to go into the basic principles behind the research so that we know how it works. And then I'm going to go into some really cool applications so that you know what kind of cool stuff you can do. Finally, some of my current challenges in grad school and the future. So first, I'm going to go through my past challenges and background. So here's a little bit of a chart of the past 8 years of my life, just kind of reflecting on the roller coaster that got me to this point. So we're going to go step by step, starting from like late high school or early community college. So the high school that I went to was built on a community college campus. It's called Norco Community College. And so I was a partial transfer student when I eventually went to my undergrad. So this is a message to transfer students out there. Yes, you can go to grad school as well. So when I was a little kid, I always wanted to like do physics and uncover the secrets of a universe. So I wanted to become a physicist. So I took a physics class at Norco College, but my first exam was a fail, 41%. So I talked to the professor and I practiced tons of problems based off of his advice throughout the quarter, and eventually aced the final and got an award from the professor. And so from there, I learned that like you can persevere even if you start off poorly. And so eventually I went to UCLA and got a lot of freedom, studying away from home and studying physics, but freedom leads to also lots of mistakes. And so I got a poor GPA during my first quarter, but eventually studied in the library a lot. I formed study groups, which proved key to getting better over time, and eventually graduated cum laude. So that showed that still perseverance is key to making it through. But in the early stages of that, I was trying to get into a research group, but in order to be able to do my dream of like doing physics research. And so it's starting in my first year, I didn't really have good credentials. I had nothing on my resume really. So, but I still tried to get into a group. So I emailed a bunch of professors, didn't really get any responses. So I eventually entered one professor's office hours cold without contacting them at all. Handed her my resume and asked if I could join her group. She told me she would let me know in a couple of weeks whether I would get in, and she didn't let me know. So I emailed her and she told me I got in. And she later on told me that the reason why she accepted me was because of my persistence. So that shows that if you keep on persisting, you can make it through. And that persistence is what eventually led me to getting published later, which was really cool. So my rest of my time at UCLA was a big juggling contest. So on the one hand, I got to be in charge of and create awesome physics clubs that help students get into research groups, and also did a lot of physics outreach. I also did some really cool publishable research, but this also resulted in juggling too many things. So one of the balls had to drop, and that ball was the physics GRE. Now note that the GRE is becoming less important every year. It's just that at the time, I didn't really do that great in it. And so I had the option of like staying an extra year at UCLA and doing better next time, or just going straight away to grad school. I wasn't really sure what to do or whether I could even do physics anymore. So I talked with one of my mentors, Professor Putterman here, and talking with him made me realize that I had tunnel vision. Like I'd only considered doing physics that whole time, but hadn't like considered other possibilities. And from talking to him, I realized that you could do really cool physics in other areas like materials as well. And I looked into the UCSB materials program and saw that they were doing really cool research. And so I applied there and I got accepted. So even if like some things go wrong, if you like open your mind up to other possibilities and talk with mentors, you can find possibilities that'll help you make it through. So how did my time at grad school go? Well, my first year was not great, to be frank. My first research group, I made a lot of different mistakes and a lot of things collapsed at the same time. I avoided tough conversations, didn't really learn very well. It helped others, but not myself, and didn't adapt to my learning. And that all of these mistakes kind of accumulated and resulted in poor grades, poor research, and me having to leave my group. So didn't really know what to do. So I took some time off to reflect, and the entire time I never gave up. Like no matter what, I decided I would just keep on trudging forward and try to figure out what went wrong. So I took the summer off and kind of just tried to think about the mistakes I made and how to make it better. And I found that reflecting on the pain is what eventually leads to progress. So some of the principles I learned was to ask questions when you don't know something. It's really important, even if you like feel embarrassed. Also to not sweat the small stuff, like a lot of different problems, little things may happen, but always put your own oxygen mask on first. To learn everything in the context of what you learned earlier. You can't really do grad school by studying things last minute. You have to build things up in an accumulated knowledge so that way you can make everything kind of add up to a whole research project. You also need to think about issues that you run into in a positive light rather than a negative light. Like rather than throwing your hands up into there like I did, try to think about problems in a positive way, maybe like a game almost, so that way like you can learn from them. And also exercise regularly. I found that jogging daily was really good stress relief. So after all this time of reflection, I came back determined to figure out what to do. And I decided to try again. So I got departmental support and took classes to explore around what I wanted to do. And I applied to several groups. I got a lot of rejections, only a couple because of credentials. Most of them were just because groups were full. But I eventually got into a group that I was excited to join, the Sanghi-Han group in the chemistry department, and the rest is history. So this is at a ski mountain, having a lot of fun. I applied the principles I learned from my previous mistakes, and I did much better in this group because of my lessons that I learned. And now I'm doing really awesome science. So this is this giant magnet that I'm now in charge of, and it's doing really cool research. So now I'm going to talk to you about that research. So the next step is I'm going to talk to you about the motivation behind the research that I'm doing. So I'd like to introduce this little why loop here. So in grad school, it's really easy to get lost in the weeds of what you're doing and kind of lose like sense of like why you're doing what you're doing. So here we'll kind of get a sense of like each step of the why loop. So that way, you know why we do each step of each step. So first, like you might have a big problem you want to solve, like climate change. Like it's a huge problem that affects all of us. But in order to solve climate change, you need to improve these different kinds of products like batteries and solar cells and LEDs to make them more efficient. But in order to do that, you need to improve the materials that they're made of. These materials have to be modified in order to make them more efficient. But in order to do that, you need to be able to see inside of these materials. So you can use these things called characterization techniques like X-rays or microscopes or a giant magnet and radio, which we'll go into a bit later. And you can use these techniques to see what's going on in these materials so that way you know what to change in order to make them more efficient. And then you can iterate things over and over again until you finally end up with a happier world where you hopefully mitigate climate change because you improved the efficiency of these systems. Now, this whole while loop can work for many different kinds of problems. Like let's say you're trying to study the brain or you're trying to study diseases, you'll inevitably come to a whole thing where like there's systems you want to study, but all of these different problems will have one commonality, which is you need a tool to be able to see what's going on in the first place and in order to improve what you're trying to improve. So within this, let's see why we want to use a giant magnet and radio in the first place. So that's what I do. So here's a little bit of an example of why you would use this. So let's say you have manganese doping inside of these materials, and you're trying to see whether or not it's clustering because that can inevitably result in more efficient or less efficient materials for solving climate change. So you try using all these different characterization techniques. But you see that the problem is that you have to see what's going on at the atomic level, whether you're getting large manganese clusters or small ones or isolated ones in the overall system. And in order to do that, apparently a giant magnet and a radio wave is one of the best ways to do that. And eventually you can figure out what's going on with that manganese. And so it's a very excellent way to see the local environment of materials. And we'll go into how it does this in the next part. So what is this giant magnet and radio waves? That is what I mentioned in the title of this whole presentation, NMR. So that's nuclear magnetic resonance. N stands for nuclear for atomic nuclei, M stands for magnetic for magnets, and R stands for resonance, which is basically just the nuclei kind of doing the same thing. So the next part, we're going to go into like how that all works, the basic principles behind NMR. So how does NMR work? Well, first you start off with a system, any kind of system for any kind of application you're trying to study, like proteins or nanotubes or water filtration or those solar cell materials that we talked about earlier. And you can have to grind it up into a powder form or into have it in a liquid form. And this all kind of shows that NMR can study a wide variety of systems, whatever problem you're trying to solve. And then you put these this system into a giant magnet, which we'll represent here. This is a magnet in our lab that we just got recently. It's really cool. And with this system, you're trying to see what's going on with the atoms inside of the material. And these atoms have a few different properties that interact with the magnet. One of them is that it lines up like a compass needle in the large magnetic field. And another is that it precesses like a top in this magnetic field. And we call them nuclear spins. So I'm going to represent these nuclear spins with this little guy over here for fun. So what do we do with these nuclear spins? We perturb them with a radio wave. And we see that when we do that, the nuclear spin changes in its precession frequency. So it changes how much it's like precessing. And when it does that, it's also changing the magnetic field around the nucleus. And that in turn changes the current that we detect in a coil over here. And that change in current results in a squiggly line signal like this called a free induction decay. And we can transform that signal into something that makes more sense, an NMR signal. And so you can see how you can perturb these nuclear spins to get a free induction decay and finally get this really cool NMR signal. And what does this information, this signal give us? Well, it can tell us the local environment around the nuclei. So we can see an example chemical system here where we are looking at nuclei in different locations in the spectrum. And we can see that depending on like how fast, depending on the local environment of the nuclei, it may precess a different rate. And so it might appear in a different spot in our NMR spectrum, and it might have different peaks around it, depending on the environment. So this is a powerful tool to peer into what's going on around the nucleus. So we can see here. But there's a problem with NMR. And that is that it has a poor signal to noise ratio. So nuclear spins tend to have a low population difference, which means that if you have nuclei at one energy and another energy, you have like about the same amount for each energy. And so since there's not much difference in the number of spins that are like in one state versus another, you can't really see, you don't get much contrast. It's sort of like if you're in a black room and like you can't see anything because everything's the same color. It's the same thing here. It's like if things at a different energy, if there's the same amount for each, then you can't really detect what's going on. And so like when nuclear spins like change in their precession or change in their energy, we get the spins flipping, but this leads to a low, but because of a low population difference, we get less flipping, and so we get poor signal. And this means that you need a very long time in order to build up a large signal in order to tell what's going on. So this means like experiments that may take like weeks or months or even years. So that's super impractical, so we don't do those experiments. So how do you fix this? Well, you fix it with the microwave. So the solution to this is dynamic nuclear polarization, or DNP for short. So what happens here is that electrons have a very high spin population difference. And because of this, they're much easier to detect. And so in order to excite those, we need to use microwaves instead of radio waves. And then we can transfer this huge spin polarization difference from electrons to the nuclei. And when we do this, we have a larger spin population difference. So we get more signal. And so we can get much faster experiments that may take weeks, may take seconds. And so this can give us more information for more systems when we use this. So that's the power of DNP-NMR. And the conditions to do this require a microwave source like this huge machine over here called a gyrotron, a giant magnet, of course, for the NMR, a polarizing agent, like manganese ions or an organic radical. This is just a source for electrons to do this transfer, and a cooling system to get this whole material to less than like minus 300 degrees Fahrenheit. So super cold temperatures are required for this. So this is a typical experimental setup for doing these DNP-NMR experiments. So now that you know like how this technique works, we're going to go into some really cool applications of it. So like one of these is for battery materials with manganese doping. So like this is an example battery material called LTO that scientists are studying to improve these materials for fighting climate change. So it's doped with manganese, not just for DNP, but also to improve its properties. And so it has oxygen in the battery material. And so we can do NMR to try to see what the environment around the oxygen is to improve the material. But when we do NMR with microwaves off, we see that we get no signal, and it would take us forever to get a signal built up to see the environments. But when we turn on the microwaves to do DNP, we see immediately that we get 2 peaks, and this is in just about like 30 minutes. And so with this really short experiment, we immediately see that there's 2 oxygen phases in this battery material. And so this information can be used to improve the material to make it more efficient. And so this shows like an example of like how powerful this technique can be. Another exotic example of this is involves like HIV proteins that you can polarize with DNP biradicals with their electrons. Now, don't be scared by this huge diagram here. You don't need to understand it. The only reason why this is here is just to show you that NMR can do really cool 2D experiments as well, where you can like make a map of what's going on. So no need to understand this, just know that like they're mapping out different kinds of structures of a protein here. And so they were able to reveal that with DNP that there's the HIV protein has a random coil structure, which helps advance research into HIV to hopefully make medical cures. And this is a type of experiment, once again, that you can't do without using DNP NMR. And another example from my own research group, it involves solar cell LED materials that are doped with manganese to improve their properties. These materials are called double perovskites. And so my postdoc in my groups, Dr. Sheetal Jain, took this really cool data of NMR enhanced signal. So enhanced signal peaks, amplitudes on the left is the y-axis, and then we are just changing the microwave frequency in the x-axis here. And so we get this really nice pattern here. And this is important because if we were getting like clustering as in manganese ions, then the electrons would be clustered. And so we would see a blob here instead. But because we don't see a blob, we see like something that's really nice and neat here. What that tells us is that we're not getting manganese clustering. And so that means that if these double perovskites are efficient, then that means that you want to have manganese that's spread out or not clustered to make them more efficient, since we're seeing that they're not clustered in the first place. So this is really cool. A way to use DNP that doesn't necessarily rely on just enhancing the signal, but rather seeing like how the change in enhancement changes with the microwave frequency you're using. So now that we've seen some like really cool applications of DNP NMR, we're going to go through some of my current challenges in grad school and the future. So how do you learn complicated procedures for simply starting an experiment? So we got a brand new magnet in our lab recently that requires this exotic way of like using manipulating helium gas flow to cool down the samples, so that way you can get them down to that minus 300 degrees Fahrenheit that I talked about earlier. Well, actually even lower than that. But this requires learning all these complicated procedures and turning a bunch of different knobs to be able to manipulate the helium gas flow to get to that low temperature. So how do you learn all these complicated procedures? Well, I was able to learn this through a few months of like a lot of practice, and also a lot of advice given by my senior grad student, Miranda, in my group. And but it still took a while. But the key turning point was kind of reading up on the fundamental like diagram of like how the helium gas flow works in this system. And so I can know how it goes from cooling system to the probe itself. And by understanding it and like understanding all the different possible things that could go wrong with this system in terms of this kind of diagram, I saw that how everything just kind of clicked after this, and like it became much faster to learn. And so it kind of means that like if you read and understand the underlying concept behind something, it can help you see this kinds of huge complicated procedures in terms of that concept and make it easier to digest. Another problem is like what do you do when you get results that make no sense? So this is what we got for sodium DNP on that same solar cell LED material from earlier. We got nothing, right? So like what do we do? So we talked with our collaborators, and we saw that like we decided, okay, maybe we need to spin the sample instead to get better results. And so that's what we did. So we went to CNSI and worked on a different spectrometer to spin the sample, and voila, we got sodium DNP. And so this shows that like if you talk around with mentors and you try other different methods, even if you get nothing at first, like you can get better results if you try different things. And so there's that. So in the future, I want to like continue improving and stuff like that. I want to eventually do have my own lab as a professor, but also do some kind of public service, and eventually neurotech, so like all sorts of different things. And I want to, I have this huge novel series that I'm planning to create one day. It'll eventually launch, maybe one day. And so there's that. So I'd like to thank my research group and Dr. Sonia Han for all of her support. And I'd like to thank the MSA for hosting these talks and for the feedback. So if you have any questions, feel free to email me and also ask questions at this talk. So thank you all for listening.
Thanks, Raj, for the really great talk. I actually learned a lot more about NMR than I've ever understood before.
No problem.
Yeah, so I guess I have a question to get us started. And then if anybody has any questions about Raj's talk or his path to grad school, yeah, please use the chat or the Q&A, and we'll get your question answered. I guess I had a question about, like, what did you think was the most difficult part about transitioning between undergrad and grad school?
So I'd say the most difficult part was kind of adjusting how my mode of thinking was in undergrad versus grad school. So it's like in undergrad, I kind of got by a lot by like studying last minute, or kind of like juggling very many different things from like clubs and organizations and like research and classes. And so it was like in grad school, it's completely different. You have to focus a lot on research. Like that has to be the main thing you do. And also I didn't really transition well with like studying last minute to studying in terms of everything you learned, you have to collect into a whole thing for like the research you're doing. Like you have to accumulate knowledge and remember stuff you learned before, not like forget it after you've learned it. So like, yeah, it's important to like get into that mode early on, like kind of learn to focus on one thing earlier on and learn to build up knowledge over the course of all your classes rather than just like forget it after you've learned it.
Yeah, I definitely agree with that. We have a question from the attendees, which is, what are you able to do with NMR data once you obtain it? What can it tell you?
So there are a few different cool things you can do with it. So one thing is that you, first of all, can compare it with like other NMR data that you get from similar systems to see like if your peak is in one location, that might tell you that your one of your atoms, like let's say your carbon atom is next to a hydrogen versus a phosphorus, and like you can kind of map out the molecule that you're looking at inside of the material. Or another thing you can do is distances. That's a really powerful thing that you can do. Like you can look at the peaks and also do like more complicated experiments to tell the distances between different atoms that and try to map out what the structure of the atom and of the material. And so you distances, also dynamics as well. Like you can get a sense of like how fast certain like atoms are spinning if they are, or like if they're rotating. If you do experiments with like more complicated nuclei, like which are called quadrupolar nuclei, that's a complicated term, but like they interact with local electron fields as well. And so this gives them high sensitivity to like motion in the material. So like you can get a lot of different kinds of information with NMR that you might not get with other techniques.
Awesome. Mm-hmm. I guess Victoria is asking, who did you go to support when you were struggling in early grad school days? Friends, family, counselors, or mentors?
So that was a big mistake that I made. So like when I was struggling in grad school, I didn't reach out for help until it was kind of a little too late. So like when I did eventually reach out for help, things were already pretty bad. So that's another thing, is it's important to reach out for help early. I think the reason why I didn't reach out earlier on was more kind of like because I felt like embarrassed that like I didn't know these basic things and all this sorts of stuff. But you shouldn't like feel embarrassed. You should always ask for help. Like everyone's going through the same thing. So it's like you'll be surprised at like how much help you can get by just revealing how much you're really struggling earlier on. But when I did ask for help, I got help from family. I thought they would be disappointed in me, but actually they were like really supportive, and that was really helpful to me at that time. I like when I took the summer off, I stayed with them and just kind of thought about things and kind of reflected, and was able to come back much fresher and much better than earlier. So friends, some of my friends, close friends, I talked to a bit as well during that time. But yeah, the big thing is that always talk to people earlier on rather than later on. But even if it's too late, still talk to people.
Yeah, grad school is never done alone, for sure. Yeah, okay. I guess final question maybe before we move on, unless there are more audience questions. Where do you see your field going in 10 years, for example?
What I see myself doing in 10 years. So it's completely different from, well, not necessarily completely different, but it's like I'm kind of at a split phase where, like, on the one hand, I want to do like professor, like I want to have my own research group working as a professor, and I want to do really cool stuff with like studying the brain, maybe with NMR. But on the other hand, I also want to do, in recent years, I've kind of found that like, and especially in the past year, I found that like, I really want to like go into public service and so on. So like, I kind of want to do a flip between like, I guess both of those, like trying to like help the community, help the world while simultaneously like also doing research. So that's something some kind of balance I'm trying to figure out still.
Yeah, definitely. All right. Thanks, Raj, for your excellent talk and talking about your experiences in grad school. I guess we'll move on now to our, for a question. Oh yeah, sorry. There's a question from Timothy. Sorry, I missed that in the chat. Could you explain more details about how you got to materials engineering from a physics degree?
Oh yeah, so how I got to materials from physics was entirely from 1 hour-long conversation from one of my mentors in undergrad. So up until that point, I was just kind of physics. But from talking to him, I realized that like you can do really cool physics research in a number of different like areas. Like you need physics in chemistry, you need physics in materials, you need physics in a lot of different fields. And so really you can do physics in different areas. And he suggested materials program at UCSB specifically because he told me that like it's a super interdisciplinary program where like you can do where the materials and like the engineering programs and the physics department all kind of collaborate a lot. And so that kind of got me thinking, well, if I'm doing materials, I can also like do a lot of physics and also collaborate in a whole different wide of range of fields. And so that's kind of like what brought me into materials. But another big thing too was my undergrad research. So my undergrad research itself was multidisciplinary, like a combination of materials and physics and chemistry. So we did like quantum materials research that was in the physics department. So I was already like exposed to a lot of material science stuff by that point. So I guess it wasn't that much of a big transition for me because like I was already doing materials related research. But it also helps. I guess looking back, that also means that like if you do interdisciplinary research earlier on, it makes it easier to like pivot and change to like other fields if you want to later.
Yeah, for sure. I will also note that I guess even in our program, not a lot of people even have a materials undergrad degree. I think there's a lot of chemistry and physics, chemie majors in our program. And we all take like introductory classes to kind of bring us all up to the same kind of speed. You know, as a materials major, I had to learn physics.
Oh yeah, definitely. Like materials is a very interdisciplinary degree.
Yeah, exactly. All right. Let's see. Okay, so let's move on to Ashley Roach, who will be giving us a talk on structural materials.
All right, thank you, Julia. So everyone bear with me for a second. I'm on a Mac, so I have to do a little finagling to be able to share this easily. So we can all just wait a second. And there we go. Okay, so everyone sees my dog? Yes?
Yes, very cute.
Okay, so I'd like to start this presentation off by introducing you to my very cute, very rude little dog, Lulu. If you hear any barking during this presentation, you have her to thank. So let's get started with my path to grad school. I think the best way to sum this up is that it's bookended by my indecision. So I grew up in Albuquerque, New Mexico, and here's a picture of the majestic Sandia Mountains that line the east side of the city. A fun fact, New Mexico is in fact part of the United States. I know this seems silly to point out, but my little brother, who's getting ready to go to grad school in Tennessee, was told by the HR department at his new school that they couldn't accept his ID because it was from Mexico. And this happened just a few weeks ago. So when it came to grad school, I didn't really know, or when it came to undergraduate school, I didn't really know what I wanted to do with my life. However, I knew I liked teaching from my job as an after-school tutor, and I knew that I liked math and physics. So the easiest next step for me was to go to college in town at UNM, where I enrolled in mechanical engineering, because it seemed to be the most broad, multidisciplinary path that I could take. I also planned to get a math minor and a physics minor because those two subjects I knew I wanted to pursue further. So early on in my undergrad career, I took a course from a physics professor that I really liked, Dr. Fields. I reached out to him after class to see if I could do some research with him, and he said yes. That's how I spent a summer doing some basic lab work supporting a project, creating a new age gas electron multiplier detector, or GEM detector, for use in a particle accelerator. So shown here in this yellow circle, this RHIC is a heavy ion collider at Brookhaven Lab. You can see just how big these are. For reference, this is an aerial shot, and those are buildings that you see there. Essentially what you do in this collider is you accelerate atoms or ions towards each other, they collide, and then around that collision point, you have a ton of detectors where you're looking for a lot of information. So I learned some really great lab etiquette basics and general engineering skills. And even though the work that I was doing wasn't integral to the project, I was able to learn a lot about the theory behind these detectors. But unfortunately, this was an unpaid position, so I had to work another job to make some money. So when the opportunity arose to work as a paid intern at Sandia National Labs, which just so happened to be in town, I jumped at the chance. The first job I took at Sandia was working as a process engineer intern with a great mentor, Lauren Lacey, who's moved up to Sandia, California now. I learned a lot about product engineering and quality control from manufactured parts ordered from local machine shops. And I was gaining great experience. I was getting great experience learning a lot about the types of jobs that different engineers and different education levels can give you within the lab. But I knew I wasn't in love with product engineering and I wanted to try something new. A great part of the structure of national labs is that you can move around between vastly different departments doing vastly different work relatively easily, which is how I was able to network my way to my second job at Sandia, working in a fundamental science division under Brad Boyce. Brad taught me a lot about the more abstract side of science, which I really enjoyed. The lab that I worked in was a materials characterization lab. It was focused largely on characterizing parts made through metal additive manufacturing. I was involved in a handful of projects, but my favorite was probably making an automated tensile tester system that could rapidly test additively manufactured tensile coupons in huge quantities to gather statistical data on additive properties. So from these two internships, I learned a few things. One was try different things and engage fully in each commitment that you make. To be honest with yourself about what you do and don't like and make adjustments if you can. And lastly, try a national lab if you can. It's great to get this type of varied experience. And for those who don't live next to a national lab, they have a ton of summer internships. So when it came time to start thinking about grad school, a huge decision, I was also planning another huge change in my life. I was scheduled to get married a few weeks after graduating. That made the grad school decision now what a lot of professors like to call a two-body problem. My husband was finishing his MBA, and I had to really consider how my personal life would be shaped by the grad school that I chose, because my husband would be dragged alongside me, would have to find a job wherever we moved and settle into. So we settled on UCSB. And were elated when I was accepted. So there was one final part to this decision, which was, what I wanted to study. I wasn't particularly committed to mechanical engineering in my studies, but I did really enjoy my work. And all of this, I realized that I was actually doing material science in my job. I was characterizing properties of a new material. And so with my mechanical engineering background, structural materials was an obvious choice for me, but I wasn't sure if I wanted to do experimental or computational work. So I was able to be co-advised by Irene and Dan to try my hand at both. Irene's group is computational and Dan's group is experimental. So I started my path to grad school with indecision and ended it as well. But for me, it worked out great because I love what I'm doing. And Dan and Irene are both fantastic advisors. So from this part of my life, I learned two big things. One, give weight to your personal life when making decisions, because the truth is that mental and physical health are important at every step of your journey, not just when you can finally start your career. And two, don't wear yourself thin. I had overextended myself with work, taking a lot of classes and extracurriculars, and it took a significant toll on my mental health. I would say to all of you that it's absolutely okay to cut back where you need to and prioritize what you care about most, even if it comes at the expense of something else. And with that, I'd like to close out my personal journey with one final piece of advice. Don't take yourself too seriously and take a few fun and silly risks. So what I mean by that is still live your life, even in grad school. You need to enjoy yourself, have fun, and don't take yourself too seriously within limits, of course. An example of this is when my husband and I first moved to Santa Barbara, we bought a $150 boat off of Craigslist and taught ourselves how to sail. Here's our little boat being beach launched, where we just wheel it up to the water's edge and push it out to sea. All right, so now let's get into the science. My talk today will be about metal defect characterization. I know I said I do both experimental and computational work, but today I want to focus largely on the experimental side of things. So these last 2 weeks, we've listened to a lot of fantastic presentations that focus on specific things like batteries or components of jet engines. So for my talk today, I'm going to take a step back and show you how research doesn't have to be focused on a specific part or application, but rather be motivated by something broad and fundamental, like the physics of how metals behave. So I want to bring us back to the structure, processing, properties, performance tetrahedron that we've been seeing in the intro slides these past few weeks. This is kind of at the heart of material science, where part performance is affected by materials processing, structure, properties, and at the heart of all of this is characterization. So for example, we saw an awesome talk last week by Victoria Christensen about components within jet engines, where the engine in this plane is labeled with an arrow, within which we saw there were some awesome metal alloys being used that have been designed to withstand extreme temperatures and chemical environments within a combustion engine. But if we zoom out and look at the entire plane, we realize quickly that the work of metals and metal design and characterization doesn't stop there. The entire plane is made of metal. That means that scientists and engineers who design and build these planes must know the properties of the aluminum alloys used in the skin and body of the wings. Another example is rockets. Specifically, here's the SpaceX Starship high altitude prototype, which has been designed with a stainless steel hull. This was chosen by engineers and scientists who looked at the requirements needed for the rocket, combed through the list of materials that could meet those requirements, and landed on stainless steel. These engineers and scientists must be pretty confident that these stainless steels will behave as expected if they're using them within rocket science, right? So that confidence is built up because of the work that material scientists and engineers have done to characterize the material. And finally, cars are something that we interact with every day that depend heavily on metals and their performance. A big area of research right now is making car bodies that are lighter without sacrificing strength, not only to reduce fuel burn for internal combustion engines, but to improve battery performance for the next generation of electric vehicles that are racing to market. Cars have, rightfully so, very strict safety requirements, which means that engineers and scientists better be extremely confident that the metals they choose or create for cars will perform as expected for decades to come. So there are a few ways that we can get data on metal properties. First, we can actually make parts and components, use them in application, and then perform a post-mortem analysis when they break or behave outside of the bounds of normal service. For things like cars, planes, and rockets, this means spending a lot of money and materials to make something that could endanger human lives, as we see here, 2 disasters. Obviously, this isn't the best idea. Instead, what many engineers and scientists do is create a model system that they can test in a controlled environment. There are many different tests that scientists and engineers have devised to measure material properties, but perhaps the most ubiquitous is the tensile test. This is an example of a tensile load frame, but it doesn't have to look like this. There can be a number of different types of equipment that you can use. The basics of a load frame is a rigid frame that doesn't move at all while you run a test, a place for your sample to be fixtured in the center here, a crosshead or actuator that moves up to actually pull your sample until it breaks. And then finally, and most importantly, a ton of great data that we gather from these tests that we can use to model how materials behave in other environments. So let's go a little more in depth on this tensile test and how it gets us material properties. And remember that we need a model system that is simplified for us to run these tensile tests. This is where this tensile specimen comes in, shown on the left here. The basics of how this works is as follows. We can see here on the right that the tensile sample is fixtured at the top and bottom by some kind of jaw or screw, whatever you decide to design, depending on the load frame, just to keep it in place. The top head moves upward, pulling the sample while the bottom is fixed. So when this head moves upward, we can measure a displacement that the sample experiences. As we're pulling, we're also measuring and recording the force that it took to pull that distance. We can then plot this force versus displacement during the test that the sample experienced that then can be used for further analysis. However, force and displacement values are very specific to this exact specimen and this exact test. So we take these values and we generalize them so that they can be applied to specimens that look different or used in completely different real world applications. So here we have our specimen that we know sees a certain amount of displacement during the tensile test. Think about if I made this specimen larger, it would probably be able to stretch a displacement that was larger too, but the material didn't change at all between the two. So how do we reconcile that if our goal is to measure material properties, not specimen geometry properties? So the feature of relevance for this displacement value is the length of the specimen. The displacement during the test is proportional to this length. We can generalize the displacement then by dividing the distance stretched by the length of the specimen. This gets us away from geometry dependent behavior like displacement and to strain, which is a material behavior. But we also have force that we measured, which is also geometry dependent. If we compare the forces between the large and small specimen during the test, the large specimen is going to be able to hold much more load, which would make the force measurements higher. But again, the material hasn't changed between the two. If we take a closer look at what's happening at the center of the tensile specimen, if we just take this little gauge section and zoom in, we can see that the cross-sectional area, or the shaded area labeled as A here running through the center of the gauge section, is the feature of interest. All load applied to the specimen is carried ideally equally across that cross-sectional area of the specimen. So the bigger the specimen, the bigger the cross-sectional area, and so the higher the force. To remove the impact of this geometry, we generalize force by dividing the force measured by the cross-sectional area of the specimen that carried that load. This gets us to a stress value that the material experienced as opposed to the force that can change between each sample. So from this force displacement curve, which has now been converted to a stress strain curve, something you may have heard mentioned in previous talks in the seminar series, we can get really important material properties. So these properties can include things like strength and ductility and so much more. And these are critical to scientists and engineers that use them to define how a material behaves, and critical when trying to predict performance of the metals in other applications. So phenomenological studies, or these studies that I've just described, where we observe material response and fit equations to it, have given us a ton of insight and have enabled us to predict metal behaviors in cars, bridges, and more. However, science has progressed, and we have moved beyond simply running thousands of tests and observing trends. We have reached the point where we can actually study the physics behind how metals deform at the atomic scale, which can really help predictions. So I like to think about this journey in terms of history. So things started off where all people could do really is observe behavior that was visible to their eyes. Like this graphic here meant to convey the classic story of Isaac Newton getting the idea for the theory of gravity when an apple fell from a tree and hit him. Then as time went on and science progressed, new equipment such as the microscope was invented, where now people could see things much smaller than our eyes could with the help of lenses, hence going down in length scale as we see here. New science was opened up with this discovery, and people learned things like the fact that we're all made of cells. And then as time and science progressed further, people started experimenting with imaging techniques using things other than visible light, like the microscope uses. People use things like X-rays and electron beams, like this that we see here. It's called the scanning electron microscope, or SEM for short. This is the tool that I personally use for my research, and I'll explain this towards the end of the talk, how electron microscopes help us in our quest to learn more physics about how metals deform. So let's get down to lower length scales. Everything is made of atoms. Here's our atom schematic, right? Where we have the nucleus with protons and neutrons, and then we have an electron cloud circling it. In animals, these atoms arrange themselves into cells. Here we see human cells. And a lot of chemicals and organic materials, they arrange themselves into complex molecules, like this caffeine molecule here. And you'll notice that these molecules are orders of magnitude smaller than these human cells. And then in inorganic things, These atoms often arrange themselves into ordered structures. For metals in particular, a very nice periodic ordering is often found at the atomic scale, where atoms arrange themselves on what can be described as a type of 3D grid or lattice. This is what's often referred to as crystal structure, and it has different ordering patterns and symmetries depending on the type of material or alloy. Often to describe these atomic ordering patterns or crystal structure, material scientists and engineers will define a unit cell, which is simply the smallest grouping that you can find in that pattern that can be used to describe the entire system if you repeat that unit cell over and over in all directions. You can notice here that the scale bar is orders of magnitude smaller again than the human cells, where micrometers or microns for short for the human cells are 10 to the minus 6 meters, while nanometers for the unit cell here are 10 to the minus 9 meters. And so with these teeny tiny sizes, it's clear that there are a ton of atoms in any metal structure. So we can imagine this crystal structure continuing vertically to the left and right and in and out of the page, on and on. So now we think about materials at the atomic scale. When we do our tension test, let's look back at that crystal structure schematic and see how this behaves. And we can think of each circle here as an atom, all arranged very nicely in a periodic lattice structure. And then we can think of each line drawn between the atoms as an atomic bond, a metallic bond, to be precise. If we try to pull apart our metal, like we do with our tensile tests, at the atomic scale, we can think of this as trying to stretch the lattice. As we do this, the bonds are going to try to fight us, right? Because they don't naturally want to be that far apart. And that means as we stretch this lattice, we're going to see the force required to cause the strain or displacement increase. So the force increases as well. So if we go back to the stress strain curve that we saw a few slides ago, and we think about how this lattice stretching relates to what we observed during our tensile tests, as we start at 0, which requires 0 strains starting from rest, as we stretch, we'll see the stress increase across this plot. However, these bonds aren't super stretchy. We can only pull them so far until they break. Remember how these teeny tiny atoms are closely spaced, and how even stretching these bonds all the way until they break don't give you a ton of displacement or strain. But that doesn't square with what we instinctually know about metals. When we think about a bike frame that will bend and warp out of shape if we get into an accident, these are huge displacements compared to this atomic level stretching. So how in the world can this be achieved atomically? How do we get the rest of this displacement we saw in our stress strain curves? Well, the answer lies in defects or imperfections in the atomic ordering of the crystal structure. So there are a ton of different types of defects that can be present in a metal lattice, things like missing atoms called vacancies, where if you have enough of these grouped together in the same area, you'll form a void or a pore. Other types of atoms taking place of the dominant atom, which is called a substitutional defect. A different type of atom occupying space in between the dominant atoms called the interstitial defect. Or you can imagine a group of atoms in the crystal that have patterned themselves in the same way, but the lattice is oriented differently from this group of purple atoms here. So the same pattern and symmetry, but now they're just oriented differently to each other. These two are called grains. This purple is a grain and this orange is a grain. And the place where they meet each other is called a grain boundary. This is another type of defect that takes up space in a three-dimensional plane between the two grains. And finally, arguably the most important defect for deformation of metals is the dislocation. The dislocation is best understood as a missing section of atoms in a particular atomic plane. So if each of these groups of atoms is in an atomic plane, a dislocation is a missing section of the plane, or what's often referred to as a missing half plane or an extra half plane, if you want to think about it that way. But how does this, that's great, but how in the world does this defect in particular change the way metals deform? Most importantly, how does it impact metal performance when used in real world applications? How does this dislocation relate back to our stress strain response that we measured from our tensile tests? And so this dislocation, as you see here, I'm just going to use this symbol from here on out. This is the symbol used for dislocations. And this extra half plane, of course, is extending in and out of the page for a long distance in a line. So back to a perfect lattice, we know that we can stretch the lattice and we get some amount of strain in the material as a result. But once we reach the limit of how far we can stretch, the lattice will eventually break. Like we see here, the bonds being broken between two full atomic planes. This is catastrophic failure. The metal is now broken and unusable. However, if we look at a lattice that has a dislocation in it, just like we saw in the previous slide, what we see here is a dislocation but it just looks a little different. It's flipped so that the extra half plane is coming from the top instead of the bottom. The black symbol for dislocations is shown now oriented differently. And you'll also notice that the lattice planes parallel to the extra half plane have distorted near the asymmetry. That's what actually happens in the material. So what's special about this defect is now, instead of having to stretch all atomic bonds in between these full atomic planes, like we saw in the perfect lattice, the dislocation defect made it easy so we can focus just on the bonds local to that patterning asymmetry, which is the edge of that dislocation, that line going in and out of the plane. When pushing or stretching on this lattice, just the bonds local to that dislocation line will break. And so depending on the direction of the pushing or stretching, the nature of this defect is such that the extra half plane will actually be shuffled to the left or the right through the material. So instead of seeing catastrophic failure with bonds breaking, dislocations allow metal to just break bonds locally around the defect, and the dislocation line will zip through the material as a response. The magic of this dislocation defect is that the metal lattice can now accommodate more strain. Dislocations are often found in metals in huge numbers. So as you load or deform the metal at the microscopic level, we have this substantial population of defects zipping through the lattice along different atomic planes, depending on the material's symmetry. And the net result is that we will begin to see much larger strain. So now our stress strain curve looks like what we saw at the macroscopic scale in the full load frame tensile tests. And that the magic of that is dislocations. So it seems like these dislocations are simple enough, right? If we can define them and describe how they behave. But the truth is that in real materials, there's billions of atoms arranged in these lattice structures. These dislocations are often interacting with a number of other defects in the lattice as they move along under load. The term that, so now you're interacting with all these different defects. It becomes really, really complicated, it becomes muddied. The term that material scientists and engineers use to define the complexity and populations of defects is called microstructure. Metal microstructures are most often full of a number of different grains or groupings of crystal directions that are all butting up to each other, forming a network of grain boundaries. We can visualize this quickly by labeling the orange and purple crystal orientations as different grains. And then let's imagine that these two grains are now no longer alone in space, but part of the microstructure of a metal, let's say copper. So we see here in this copper, we see a collection of different grains. All the different colors show different orientations of this same patterning. And so remembering that the atom types and the patterning aren't different between the grains, just the orientations relative to each other. And there's a distribution of shapes and sizes of the grains, and there's a network of grain boundaries separating each unique grain. So this collection of defects, namely these grain boundaries, don't have to be the only types of defects in the microstructure. We can also imagine this copper as having a certain density of dislocation defects using this line symbol that I've used before. And they're there to help the metal deform, but now they have a number of obstacles. In this case, grain boundaries, different crystal orientations, and other dislocations that are going to impact the way these dislocations can move and accommodate strain. So now we can see how things can get muddied really fast. With huge populations of grains, dislocations, and other defects, material scientists and engineers have their work cut out for them, investigating how different types of metals deform, how processing approaches change these microstructures and the resulting deformation behavior, and how we can create new materials and alloys that will deform in different and desirable ways. So let's get into the nitty-gritty just quickly on how we actually do this at the small scale. And so we know the goal is to observe how microstructure and material, including things like the specific lattice patterning and levels of symmetry, impact how metals deform. So we need to go way down in length scale, perform tensile tests at the micro and the nanoscales. With small samples and high-tech, high-resolution data capturing and imaging, we can observe these dislocations directly and watch how they behave in different circumstances. Then we take what we observed, compare it to theory, and we can compare it to theory that we all agree upon and determine if things are different than expected. At the heart of these small-scale mechanical tensile tests is this FemtoTools mechanical testing system. This is basically analogous to our load frame that we saw at the beginning of this talk, with the force sensor on one end to capture the load of the sample, and actuator on the other end. The sample goes right in the middle here. And we can think about this just like we thought about how the sample was fixtured into the load frame earlier. There's some cool, unique things about these smaller length scales, though, like this push-to-pull device that is used to transfer load from the sample that comes from this larger system. So this probe that's used to actually cause deformation is around 2 microns, or 10 to the minus 6 meters at the tip, which is still very big for our tiny little samples that we're testing. So to transfer motion from this relatively large probe to a very, very small sample in a controlled manner, we use the push-to-pull. So these work kind of as follows. The blue part is rigid while the red part can move. When you come in and push that button on the left that we see here on the push-to-pull, we see the red part shift while the blue part is stationary. So as these two move relative to each other, there's a specimen right here, a teeny tiny specimen in the center that will actually see a net tensile displacement. That's how we can get really controlled motion for these very small samples. If we look at the scale bar here, this 5 microns sample, the width of the sample is about 5 microns. Compare that to a human hair, which is about 75 microns wide. So this is very, very small. It's pretty cool. And so I just want to do just a brief plug on how we actually do this, which is electron beam imaging. UCSB has some great microscopy facilities. I won't go into too much detail on how this works, but I just kind of want to compare it to what a microscope can do. So we've heard the word SEM mentioned a few times. Why are they useful? The big benefit, of course, to an electron microscope is the resolution. For the SEM that I most commonly use, the resolution is about 0.8 nanometers. It's super, super tiny. The theoretical limit of electron microscopes is, of course, much, much smaller, but I won't get into why those are different today. So basically, to understand how these work, we can contrast them with the Hubble microscope, where a microscope works by shining light to a sample, and then the image of that sample is focused by a number of different lenses, and at the end it makes that image big enough that a human eye can see it. And SEM works kind of similarly if you just kind of think about flipping it upside down. So now instead of a light source, we have an electron source. And now we have this column where there's a number of different lenses that are focusing and changing that beam. But instead of making an image bigger, what we're doing is we're making that electron beam really nice and clean and focused and centered so we can get really good images. And then as it comes down to the sample, what's happening is it's actually absorbing. So this is our electron beam here, unlike visible light where it just kind of, diffracts off, and what you're seeing is kind of the negative of how that light interacted. For an electron beam, the electrons actually absorb into your sample, and they'll go in, and if we remember our schematic of an atom, what's happening is these electrons are going in and they're actually adding energy to these atoms. They're exciting these electrons around each nucleus of the atom. They're shuffling things around, kicking things out, making them higher energy. And then once everything kind of settles down, new electrons are actually ejected. Some of them are called secondary electrons, some of them are called backscatter electrons, and that's actually what the detector sees. And so that's kind of how electron imaging works in a nutshell. I also want to point out that X-rays are generated in this process, obviously dangerous to human health. So you want to make sure that any imaging system that you buy or make has proper shielding, radiation shielding. And so if you want to figure out how transmission works, I can go through that, but I just want to end with reminding you that the goal of this is part performance. So we started with our tensile test to get material properties. We shifted that down to smaller length scales so that we can look at physics instead of just broad material properties. And then we use those small scale tests to look at how microstructure impacts the material properties. And all of this is coming together reminiscent of our materials property processing tetrahedron that we started off with. So with that, I'd like to end and take just a few questions if we have time for it. I went a little long.
Thanks, Ashley. That was a really good talk. I guess while we wait for questions in the chat or in the Q&A, I guess I'd like to ask what you think, or if you can talk about the experience of finding 2 advisors in grad school and how it's like managing, 2 professors, I guess. Not you managing, but you know what I mean.
So I was a little lucky that both of my professors also work really well together and are on other projects together. So it was a really easy thing to just go, hey, I liked talking to Irene, I liked talking to Dan, they kind of talked to each other, they had a project available for me. So it just kind of happened pretty naturally. I know that a lot of people in later years in their grad program can also become co-advised because maybe they see the direction that their project is going on, that they're really interested in, and they say to their advisor, hey, I think we could really benefit from the expertise of this other professor. Could we maybe bring them in and maybe do a co-advisement? So that's totally possible. And then I think being co-advised, it can either be double the work or no work, right? Because both of the advisors assume that the other one is giving you stuff to do, and so you end up doing nothing. So I think just knowing that you're able to bring things up to both of them or individually, whatever, just knowing that you can keep that dialogue open of saying, hey, I don't know what to do, or hey, I'm stuck in this problem, whatever it is, just to keep things moving and keep them interested in you, right?
Right.
So.
Yeah, okay, cool. Let's see, looks like we still don't have any questions in the chat. So I guess another thing I wanted to ask was, I mean, this is something that we probably all struggled with applying to grad school, but how did you, like, what did you look for when you were applying or choosing schools for grad school to like kind of ensure, or like at least try to like get the best chances of having some kind of work-life balance?
Yeah, that's tough. Admittedly, I didn't do great my first few years here. It's really something that I think most of us don't realize that we're doing poorly until we're in the thick of it and, you know, feeling bad. And so I would just say, you know, you're kind of on the path to the rest of your life, right, in grad school. So you can, you know, put your head down and work really hard and just try to get everything pushed out so that you can move on to the next step. But then you're kind of setting the pace for the rest of your career. And so you just kind of have to take a step back and assess, you know, what level of stuff can I do that I can imagine doing this level of things for 20 years, you know, and then that's kind of a way to pace yourself and not be so gung-ho about getting everything done at once or meeting all these deadlines that you set for yourself, all of that, if that makes sense.
Yeah, and I guess Caroline has a question in the chat. So you said you worked on both experimental and computational stuff. So have you decided whether you want to keep doing experimental and computational stuff, or, you know, one or the other, or something else entirely?
I have not decided. The truth is that I think I'm going to look for something interesting. I want to go into industry because I want to stick around here in Santa Barbara because we love this area. And then I want to try to teach at, you know, City College or another community college in the area. And so that kind of opens things up to just, you know, I'll do whatever I have to, whatever is interesting, a cool project, whether that's computational or experimental. I have more history in experiments, and I feel like I'm more just physically intuitive in that aspect. So admittedly, I'll probably be drawn towards experiments, but modeling is super cool.
Yeah, and I guess kind of a related question, do you find it hard to kind of juggle like you know, sometimes it feels like there's very different like knowledge spheres between computational and experimental. Like, can you talk about, you know, doing both in grad school?
Yeah, it is tough. I would say where I'm most successful is if because when I started off, I tried to say like, oh, maybe, you know, Mondays and Tuesdays are working in the lab, and then Wednesdays, Thursdays are working on the simulations, but that's a lot of scattering, right? And that kind of stresses you out. So I just finished a residency with Los Alamos National Lab, and in which I dedicated, you know, 3 months to, I'm just doing computational work, which I think is much easier if you just kind of break it apart into big chunks of, you know, I'm going to do enough work to get a paper in one aspect, and then I'm going to kind of shift gears. And so now during the summer, I'm going to work on these tests that I talked about, kind of shifting gears. I think that's the best way I've been able to handle that.
Yeah, I can definitely relate. I mean, even
Yeah.
I just do experiments and I'm just like running in between lab and like doing work at home.
Yeah, it's tough.
All right. I guess since we're a little over time, we'll end here if there's no more questions. But yeah, we'd just like to, thanks to both of our speakers today. I learned a lot today myself, even as a grad student. So I hope you guys enjoyed their talks. And just like to point out that next week we have 2 other speakers for our final segment of the seminar series. Vince and Lily, who will be talking about efficient LED materials and materials for quantum computing. And yeah, And if you guys want to see any recordings of past or future seminar series, we'll post them on our YouTube channel and the link is in the chat. All right, thanks everyone. Hope to see you next week.
Thank you.